Example 4, with all of these expectation and probability distribution ones, it makes sense to first draw our probability distribution table. So I chose a value of k to represent the probability of 1 and 2, and then it says the value 3 is 3 times as likely, so that would be 3k. Yes?
In my book it says 2 times as likely.
It says 2 times as likely in yours, and mine says 3 times as likely? Okay, we'll change it to 2 times as likely. That'll change my answers a little bit, but that would make this 2k. And then when you add it up, it's going to be 4k equals 1. And the probability, finding the value of k is going to be 1/4. And then my numbers here are going to be slightly different because they will all be over 4. And this will be, there we go. So these will all be over 4. And 2 times as likely will make that 2 over 4. Adding those all up, 6 plus 2 is 8 plus 1. You get 9 over 4, 2.25? Yes? Oh, you just took a random guess and figured it out it was 1 over 4. And in this case, it's easy enough to do that, right? Like the numbers aren't that hard that you could do that. When the numbers get harder, then the algebra is the nice way to come up with that value. So in this case, there would be no deduction for saying, I just figured it out, it was 1/4, because that mental math isn't hard. All right, no different numbers on this one? So again, set up your probability distribution chart. And then from that, once again, you can solve for the value of k. And once you found out k, check if you got your expectation right. The expectation should be 3. Now I like this last example. There's 2 ways you could set this up. One way, and what I did, is I took the $5 off already when I set up my probability distribution chart. So if it happened to hit the 15, you actually only make $10 because you've already spent $5. If it happens to hit the 1, you've actually lost $4 because you spent $5 to play, and then you won $1 back. Okay? So I put the values in there with the $5 included. The other way you could do it is you could do it without that, figure out your expectation of what you would win from the spinner, and then subtract $5 off of that at the end. That will give you the same result. Okay? If I was setting this up as a game where I wanted to take people's money, I would do it this way. Because according to the spinner, what are your chances of winning money? 3 out of 4 times you win money. Technically, from the spinner, you win money. You've already spent your $5, and then you win $1. And everybody can cheer. But you've actually lost $4, right? So what's the expectation of this? Well, they're each 1/4. Taking all of those values put in together ends up adding up to -3/4. So if we played this game in class, chances are that on average, every time I'm going to make 75 cents. So if we played it 10 times, I should make $7.50. Okay? One of the when things are evenly split up like this, one of the things I like to do sort of mental math-wise is I like to say, okay, theoretically, if we play it 4 times, each of the 4 things should happen once. So if I played this 4 times, I'd get 15, I'd get 10, I'd get 1, I'd get -9. Adding those all up, 26 minus 9 would be, is that right? 26 minus 9 is 17. And I would have spent how much? I would have spent $20 paying it, right? Does that make sense? So I would have made 17, but I would have spent $20. So after 4 times, I should be down $3. What's my expectation then? Down $3 over 4 times, 75 cents a time. So you can do that kind of mental math to check something like this to see if it makes sense. Okay? Deceptive though. Because it looks, when you see this game, doesn't it look like you have a better chance of winning things than not winning things? And in fact, there's only one bad one. Your mind would say that. There's only one bad one. Because that $5 is not included.